This is going to cover lesson 2, which is about the second grouping of macromolecules, which are lipids. And let's open this up. We're going to be answering under Unit 7. We're going to answer lesson 2 questions since we're doing lesson 2. Okay. So, lipids are commonly called fats. Their main function is long-term energy storage, but they also have a couple other important uses or functions as well. They're also used as steroids, which are signaling molecules in the body. And they're also, I don't know why I didn't put it on here, but they're also make up cell membranes. So when we talk about cells in semester 2, the barrier between the inside and the outside of a cell is made up of lipids. So they're very important in that as well. They are the building blocks or the monomers for lipids. There's actually 2. So they're made of fatty acids and glycerol. So the structure isn't going to be as repetitive as carbohydrates were, but there's still some patterns that we see in that they usually contain these things. Some examples of polymers of lipids are triglycerides. That is fat. Like when we usually use the term fat, and what we usually think of, this is what those actually are more specifically. Since fat is a term for broadly for lipids, if you're thinking of specifically fat within a body, that's triglycerides. Cholesterols are a type of lipid, and then phospholipids. These are those molecules that make up the cell membrane, which is the barrier between the inside and outside of the cell. Kind of analogous to your how your skin is the barrier between the inside and the outside of your body. So for cells, that's phospholipids. So here are the structures, the atomic level for fatty acids right here, and then glycerol on the top right. So when we said the building blocks are glycerol and fatty acids, this is what they look like. The fatty acids have a ton of carbons bonded together and then filled in with hydrogens. And then they have this CO, that's a carbon double bonded to an oxygen, and then that same carbon bonded to an oxygen and a hydrogen at this end where it will connect to the glycerol, which is over here. You don't have to memorize these structures, but we will talk a little bit about this hydrocarbon chain of fatty acids because it gives fats different properties depending on the structure of this chain. So here's a triglyceride molecule. As I mentioned earlier, this is what we usually are thinking of when we hear the term fat. So type of fat found in your blood, and when you eat, your body converts calories it doesn't need to use right away into triglycerides. So here I've outlined the glycerol part of the triglyceride, and then these parts over here are the fatty acids. So the triglyceride name makes sense that this is the glycerol molecule or glyceride. That's where that comes from. And the tri, right, is because there's 3. So there's 3 fatty acids and 1 glycerol. Now the first 2 fatty acids are straight, and you'll notice that the last one is bent. And the reason the last one is bent is because of this double bond here between these carbons. So if we counted all the hydrogens on the other fatty acids, so let's do that real quick. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there's 19 hydrogens on the top and middle fatty acids, but the bottom one is missing 2 of them, right? There's no hydrogen here and there's no hydrogen atom here. So we would say that this fatty acid is not saturated. It does not have the maximum number of hydrogens that it could, okay? So if it is not saturated, that means the other term for not saturated is unsaturated. So you may have heard of unsaturated fats, and they're fats that have these double bonds. And it makes the fatty acid bend. And we'll talk about some why that's important in a little bit. Whereas saturated fatty acids, like this middle one and the top one, these are straight. Okay. So the difference between saturated and unsaturated fatty acids, we already talked about. So fatty acids that are unsaturated or missing hydrogen atoms have a bend, and this prevents these molecules from being able to pack tightly next to each other. Think of trying to fit as many people as possible into a room, but they're sticking their elbows out. That's like what happens with unsaturated fats, is that you can't pack them tightly together because they have these bends. Versus if they didn't have the bends, if they were all saturated, if the fatty acid tails were all saturated, then you could pack them very closely together. And why is that important? Well, it makes a big difference in terms of the health of the fat. So foods that contain more unsaturated fat tend to be liquid at room temperature. Again, because those molecules can't pack tightly together, so it's harder for them to solidify. Whereas those that are saturated fats tend to be solid at room temperature. And you can see that butter is an example of saturated fat. It tends to be solid at room temperature. Whereas another type of fat, olive oil, is liquid at room temperature. And you probably are aware that olive oil is a lot healthier for you than butter, right? And it, again, is having to do with the fact that those won't pack tightly. So there's some health advantages to the unsaturated fats. And the saturated fats tend to be the worst, not associated with any, with healthy outcomes. Okay, so, and I'll just point out here, when we think of fats or lipids include fats or also oils. Things that are like kind of greasy are going to be things that are types of lipids. This is the only group of macromolecules that is like water resistant. So they usually have like a greasy feel because they don't interact with water. If you pour oil into like water, it won't dissolve, and that's because it is hydrophobic. Not seeing, I feel like I usually talk about this property. Here it is. Okay. So let's jump to this. Fats are hydrophobic. This means that they do not mix well with water. So here you can see vegetable oil being poured into water, and it simply isn't going to dissolve because that oil is going to want to interact with each other and not interact with the water. Water is very polar, and fats and lipids are not. Polar molecules like to interact with other polar molecules, and non-polar molecules prefer to interact with non-polar molecules. So the lipids won't dissolve in water, unlike the other 3 kinds of macromolecules that typically do. I maybe should have discussed this first, but polarity is like some molecules act kind of like magnets where they're attracted to certain other molecules. And like I said, polar molecules are going to have slight positive regions and slight negative regions. So they'll want to interact with other polar molecules, which also have slight positives and slight negatives. And they'll line up the slightly positive next to the slightly negative because those will attract, right? Opposites attract, just like with magnets. So fats are nonpolar molecules and they do not mix with water. We call them hydrophobic, water fearing. Hydro means water and phobic is fearing. Okay. So if we go, let's check in on our little worksheet here. You guys have number 1, true or false. polar molecules have slight positive and slight negative parts, which make them attracted to other polar molecules. This would be true, right? Polar wants to interact with polar, and polar molecules, as it says right on the slides, have slight positive and slight negative regions. Question 2. Molecules that are nonpolar do not interact with water molecules. Therefore, these molecules are also called blank molecules, meaning they are water-fearing. This would be hydro for water and fearing phobic. So hydrophobic would go in this blank. I don't want to get into all of those. So I think just those two parts for right now. Okay, let's go back to the slides. So you just have to answer those two questions in the worksheet. The rest is not something we're going to get to today. All right, let's go back to, I do want to talk about cholesterol, and because it's a super important molecule. I'm sure you've heard of cholesterol when someone's talked about, their amount of cholesterol they have in their blood. If they have high cholesterol, typically, right? A lot of people do, and it's not a great thing for your health. It can have some complications. So cholesterol is a type of lipid, and it's an important signaling molecule within your body. And there are actually two types of cholesterol, though. One is good for you and the other is bad. So when you hear someone say like, oh, I have high cholesterol, they're talking about they have too much of the bad kind. Or maybe they don't have enough of the good times, because they do kind of balance each other out. So if you have kind of high bad cholesterol, but you have a good amount of good cholesterol, you might not have problems with your health. But you obviously want to reduce the amount of bad cholesterol and increase the amount of good. So LDL stands for low density lipoprotein. Lipo is lipid, right? Just like liposuction is fat, right? So lipids are fats. Lipo here means that it's a lipid. Protein is that the other part of this molecule is, a protein, but we're treating it for all intents and purposes in this class. It is simply a lipid. Low density, this means it's actually larger than the other type of cholesterol. So LDL, low density lipoprotein, is it's like ballooned out, it's big. Whereas high density lipoprotein, the HDL, these ones are smaller. High density, it's more compact. So same molecule, but it's kind of more compact and squished together. Whereas the low density is really ballooned out and very large. Which one do you think is worse? It's going to be the LDLs. Because they are larger in size, they're apt to get stuck on the walls of your blood vessels, which is bad. That can lead to heart attacks or strokes. So high levels of LDL are not good for your health. They are a risk. Whereas, let's talk about how the HDLs are good. So LDLs are bad, but HDLs are really small. So they don't get stuck on the walls of your blood vessels, and actually they help push LDLs from the walls of your blood vessels. So they actually help kind of keep your blood vessels clear and prevent LDLs from sticking together. So high levels of HDL cholesterol are actually good for you and reduce your risk of heart attack and stroke. Here's a representation of HDL and LDL. You can see how the LDL is bigger. I have different composition of within their membranes, but that's really beyond the scope of this class. So for our classes, HDLs are smaller, LDLs are bigger, and you can kind of see how here, I don't know why they didn't do the size correctly. Like all these blue ones should be smaller than the yellow ones, but whatever. So the blue are going to be able to keep the arteries clean. So you have a lot of good cholesterol. This blood vessel looks nice, and there's not plaque built up. This person would not be prone to a heart attack or a stroke. Their blood vessels are quite clear. We would not expect to see a blockage in there. Whereas someone with a lot of LDL and not a lot of HDL, they're getting a lot of buildup of LDL on their walls, as you can see, as this like plaque buildup, basically. That's the LDL all squished together against the wall of the blood vessel, and it's making it really likely for a clot to occur, for a blockage to happen, leading to heart attack or stroke. So this person needs to reduce their LDL, and it would also be helpful if they increased their HDL to clean up their blood vessels, and have a healthier chances. And I think that's pretty much it. This slide here shows us some other structures of cholesterol, glycerol, fatty acids, triglycerides, and a sorry, that's just a triglyceride again. Kind of looked like a phospholipid for a second, but it's not. So this is just another representation of that. This is probably a little bit beyond what we want to get into, but anytime you see a bend, that's where a carbon is located. Then we just kind of assume there are hydrogens there. But you don't need to memorize that. Just, if you're curious, I can talk with you about how to read these diagrams. It's kind of cool. But you can see the saturated versus a monounsaturated fat, which only has one bend, or polyunsaturated fat. So obviously the polyunsaturated fat has multiple bends, and so this is the healthiest type of fat. Monounsaturated fat is better than saturated, but not as good as poly, and saturated is the worst. So eating a lot of saturated fat tends to increase the amount of LDLs, whereas eating polyunsaturated fats and monounsaturated fats increases the levels of HDLs. So when we talk about, why olive oil is healthier, it will increase these two, whereas butter will increase, has a lot of saturated, so it will increase the bad type, the LDL cholesterol. Those are highly related. I think that's pretty much it. So here's some more examples of the lipids. Triglycerides, which we covered a little bit. Cholesterol, we talked about. Phospholipids we didn't, but we will talk about them in detail when we talk about cells. So you'll see those in the future. And then also any oils and waxes will be lipids. They'll fall into that macromolecule category. So you can think of like beeswax, or if you like wax your skis or snowboard, those are a type of lipid. You'll notice that they don't interact or dissolve with water. So that's a really easy test to figure out what things are lipids and which things are one of the other types of molecules. And that's it. Have a nice time. I'll see you guys soon.